All right, next set of examples I'd like to look at are applications of torque equals I alpha. And so we already saw that the cylinder wins the race with the thin disk if they both are rolling without sliding down an inclined plane. What I'd like to do now is show how to calculate the acceleration of the center of mass for a cylinder as it rolls down that inclined plane. And we'll see that that is a function of the moment of inertia, so that it will be different for the cylinder than it would be for the thin ring. And so this is going to involve solving two equations. One of the equations we want to solve is the sum of the forces equals mass times acceleration. And so we can look at all of the forces that are acting on the cylinder. We first of all can act through the center of mass with a force that is equal to the weight. So then that force is going to be decomposed into x and y components, where we can define the positive x direction to be down the incline and the positive y direction to be perpendicular to the incline. And so the component then of mg that acts through the center of mass is going to be mg sine theta, just like it was before for a non-rotating mass. It has that component of force, but here we should put it right through the center of mass, realizing that that force is acting through the center of mass. So we have mg sine theta. And then the component of the force which is opposed by the normal force is going to be mg cosine theta. And so we have one other force acting here, and that's the force of static friction. And so that's what causes this mass to rotate, is that it's going to tend to want to slide this way, but the static friction force acts to oppose that. And so this is F static. So we might wonder then, well, is that F static maximum? Or in other words, the coefficient of static friction times the normal force. And the answer is not in general. When we have this cylinder, and let's just go over to the incline here and take a look at this. When we have the cylinder rolling down the incline, we're not pushing the static friction force to the breaking point until we increase the angle considerably. So eventually we'd reach a point where we'd have some sliding and some rolling. But here, we're in a pure rolling mode, and the static friction force is unknown because we do not know how close to the maximum force of static friction we've pushed the system. And so therefore, F static is an unknown in our equations, and it's not equal to the maximum force of static friction. So what we can do here for F equals ma is write mg sine theta for the sum of the x forces equals mass times x acceleration minus the force of static friction is equal to ma. And so that's our first equation. Mg sine theta minus our force of static friction equals ma. But this is unknown. You'd be tempted here to maybe write the coefficient of static friction times the normal force, which would be mu s times mg cosine theta. But that would be wrong because we haven't pushed the static friction force to the point at which it starts to slide. And so with this as an unknown, we need a second equation to solve for the two unknowns, the static friction force and the acceleration. That's going to be the sum of the torques, and we could have more than one, equals I alpha. Okay, and so what we need to do then here is to choose a pivot point. Okay, and so what I'm going to do is I'm going to choose the pivot point to go right through the center of mass. And the reason for that is that I know what the moment of inertia of the system is about the center of mass. And I may not know what the moment of inertia is if I cause it to rotate about some other point other than the center of mass. I know that I is 1/2 mr squared from the center of mass, so I'll choose that as my pivot point because I know the moment of inertia at that point. Now I'll show you how to calculate the moment of inertia about some other point in an alternative way to solve this problem in a few minutes. But we'll do it with the center of mass of this system being the center of spin. Remember, you're free to choose any point you want as your pivot point, as long as you stay consistent with the equations. So with that as our center of mass position, notice that the normal force goes through that point, the weight force goes through that point. The only force that's acting on the system that doesn't go through that point is the force of static friction. So we can then write that the force of static friction, S times R, is the torque. And that's going to tend to make this thing want to go clockwise. Here's our radius vector. Here's our force of static friction. All the other forces intersect with the center of mass position, and so this is the only surviving force. This gives us a condition on the force of static friction. So this is the torque, F static times R, equals the moment of inertia. So that's going to be 1/2 mr squared times alpha. But alpha we can write in terms of the acceleration of the center of mass as being equal to A over R. So we already saw that there was that correspondence between the tangential acceleration and the angular acceleration. So I'll write this then as 1/2 mr squared for I times alpha, which we'll write as A over R. So now what we have is an expression for the static friction force that is a function of the acceleration, which we can plug back into equation 1. And so if I work this thing through, I see that F static times the radius equals 1/2 m. One factor of R cancels, so we get 1/2 mr A. And then we cancel out the r's. We get the static friction force is equal to 1/2 ma. And this A, even though it's the tangential acceleration, is also the acceleration of the center of mass. How do we know that? Well, let's go back to our cylinder. Let's imagine that the cylinder has a bunch of string wrapped around it, and that I unroll that piece of string from the cylinder as the cylinder rolls. Then in a certain amount of time, as this cylinder unrolls the string, the length of the string is going to be equal to the distance moved by the center of mass. And so therefore, the displacement of the center of mass and the displacement at the surface of the cylinder must be equal. And if it's equal over the same length of time, that means the velocity of the center of mass equals the tangential velocity, and the acceleration of the center of mass must equal the tangential acceleration as well. And so this is our justification then for stating that the tangential acceleration is the same as the acceleration of the center of mass in this equation. Okay, so you may want to rewind that if I went too fast with that explanation, but you can always email me with questions, and by next week I should have something set up on Zoom so that we can actually talk. I'll get that figured out during the spring break. Okay, so we'll plug in the static friction force into equation 1, and that gives us mg sine theta minus 1/2 ma equals ma. Or mg sine theta equals 3/2 ma. And so now we can solve this for the acceleration. And so the acceleration then is equal to, the masses will cancel, meaning that the result does not depend on the mass, equal to 2/3 g sine theta. So for our problem, let's set the angle equal to 30 degrees. Then the acceleration would be equal to 2/3 g times the sine of 30. sine of 30 is 1/2. And so this would be equal to then 2/6 g, or g over 3. So this would be our general expression for the acceleration, but for the angle that we have in this problem, then the acceleration would be 1/3 the acceleration due to gravity. Now, what I'd like to do is show you another way to solve the same problem. But in order to do it, we're going to need to choose a different pivot point that is not on the center of mass. I'm going to choose a pivot point that's here, instead of a pivot point that went right through the center of mass. I'm going to rework the same problem. And I better get the same answer. If I don't, it means that I did something wrong. I'm going to choose this pivot point rather than the pivot point that went through the center of mass. We still have the same forces acting as we did before. Here's the mg force. Here's our mg sine theta force. Here's our normal force. This is mg cosine theta. And here's our force of static friction, Fs. Okay? And so what we can see then is that if we choose this as our pivot point, then all of the forces are going to intersect except for the perpendicular component of mg. The static friction force intersects with that point, mg cosine theta intersects with that point, and the normal force intersects with that point. And so none of those are affected by the torque equation about this pivot point, except for mg sine theta. But the big trick here is that because we've chosen that as our pivot point, we need the moment of inertia about this point and not about the center of mass. So how do we do that? Well, in general, we have what's called the parallel axis theorem. So this tells us that I, about some other pivot point, by other, what do I mean? I mean other than the center of mass, is equal to I center of mass plus md squared, where d is the distance from the center of mass to the pivot point. And this is, again, called the parallel axis theorem. So why is it called the parallel axis theorem? Well, here we have our axis of rotation through the center of mass, and so we want to move that axis parallel to itself a distance d. Okay, and so that's what I'm doing here. I'm moving it a distance d so that now I'm pivoting about the outside edge of the cylinder rather than through the center of mass. And so we can think of this then as being what the moment of inertia would have been through the center of mass, plus by moving the pivot point that far, we could think of it as being an extra term that is like moving a point mass by a distance d. So if we do that for our cylinder about the new pivot point, then the d value is just r. So this is our new pivot point. And so we'll have I center of mass as 1/2 mr squared, as we saw before, for cylinder, plus m times d squared, but d is r in this case. So that gives us 3/2 mr squared for the total moment of inertia about this new pivot point. And so this is the key. When I have given exams in the past, what I have found is that if I ask you to calculate the torque or the angular acceleration or whatever it is that's asked for, a lot of times you'll choose that as the pivot point, but then not use the parallel axis theorem. And you pretend that it still is as if it were being rotated about the center. And that would be considered a major error if you did that on on this problem. And so what we end up with here then is torque, that's mg sine theta, multiplied by r. Okay, so here's our radius vector from the mg sine theta. That's the only part of the force that doesn't intersect, remember, with the pivot point, where the extrapolation of that component, mg cosine theta does, but not the sine theta component. So that's a torque equals I. So now for I, we need to plug in 3/2 mr squared times alpha, which again we'll call A over R. And so we'll notice here then that the m's will cancel and the r's will cancel, just like before. So here we have an r squared and an r canceling. So we get mg sine theta r equals 3/2 mRA. Cancel out the m's, cancel out the r's, and we get, which is kind of comforting, the same answer, 2/3 g sine theta that we got doing it the other way. So if this angle were 30 degrees, then this would again be equal to g over 3. So this is our alternative approach. And so this then involves changing the pivot point. And so on previous exams, I have actually asked you to do it both ways and then show that your result is the same. And it should be, because you're just solving the same problem two different ways. Okay, so that is an illustration then of how the parallel axis theorem is used to change from a pivot point that goes through the center of mass to one that is located at some other position.